grab the sources you've sent over and, well, really try to understand them.
Get stuck in.
Exactly. And today, you've brought us a truly mind-bending topic, cosmic inflation. Okay, let's unpack this.
That's a big one.
It is. We're looking at a theory trying to explain the very, very first moments of our universe, its origins, how it potentially solves some huge cosmic puzzles.
Yeah, some real head scratchers in the standard Big Bang model.
Right. And the ongoing, pretty intense search for actual proof for observational evidence. So our mission today is to guide you through this, pull out the key ideas, maybe some surprising facts about how it all might have kicked off.
What's fascinating here is it's not just what happened, right? It's why it matters. How this fraction of a second potentially shaped everything we see today.
Yeah, it connects the quantum world to, well, the entire cosmos.
Pretty much. It's quite a story.
So let's set the scene. For a long time, the hot Big Bang model, the HBB, was a massive success, wasn't it?
Oh, absolutely. A triumph. It explained cosmic expansion, the cosmic microwave background, that leftover heat.
The fossil light, yeah. And how much hydrogen and helium we see. It was brilliant.
It really was. It told us how the universe evolved from that hot, dense beginning.
There were these foundational cracks starting to show. It didn't explain why the starting conditions were so specific.
Yeah.
So perfect, almost.
Exactly. That's the core issue. Cosmologists realized they were basically assuming these exquisitely fine-tuned initial conditions. Like setting the universe's dials with unbelievable precision just to get the cosmos we observe.
Which feels a bit arbitrary, unsatisfying.
Deeply unsatisfying for physicists, yeah. It led to this feeling of unease, this crisis of initial conditions. Why was the universe so special from the get-go? It felt like an incredible coincidence.
So inflation comes along.
Right. Proposed as a kind of dynamic prequel to the hot Big Bang. The idea was to make these initial conditions seem, well, natural. Expected outcomes of some earlier process, not just assumptions we had to plug in.
Okay, and here's where it gets really interesting. Inflation's power move, essentially, is solving three huge HBB problems with just one idea.
One single elegant mechanism, yeah.
A ridiculously brief, faster-than-light expansion of space itself. We're talking, what, between 10 orders and 10 seconds after the absolute beginning.
Something like that. An infinitesimal slice of time, but with enormous consequences. Just mind-boggling speed and scale.
Let's tackle the first puzzle, then. The horizon problem. Okay, so we look out at the CMB, this ancient light.
And it's incredibly uniform. Temperature's the same everywhere to like 1 part in 100,000. Astonishingly smooth.
But here's the kicker. Take 2 points on opposite sides of the sky. When that CMB light was emitted about 380,000 years after the Big Bang, those two regions were too far apart.
They were outside each other's causal horizon. Light, information, heat. Nothing could have traveled between them to even things out.
So how did they end up at the exact same temperature? It makes no sense in the standard picture.
It's a fundamental contradiction without something like inflation. Inflation solves it pretty neatly, actually. It says, wait, back before inflation kicked off, the region that would eventually become our entire observable universe was absolutely minuscule.
Tiny enough for everything to be connected.
Exactly. Small enough to be causally connected to reach thermal equilibrium. Everything was the same temperature because it was all effectively in the same place,
Okay.
Then inflation hits. Whoosh! It stretches that tiny uniform patch by an unimaginable factor, making it enormous almost instantly.
And that initial smoothness gets stretched right along with it.
Preserved across these vast cosmic distances. So the uniformity we see in the CMB today is just the massively inflated echo of that initial tiny connected uniform state. Problem solved.
Okay, that is elegant. All right, puzzle number 2, the flatness problem. This is about the universe's overall shape, its geometry.
Right, measured by this parameter, omega, AOA. And observations tell us AIA is incredibly close to 1.
Meaning the universe is remarkably close to flat, like geometrically flat, like a sheet of paper on cosmic scales.
Which sounds simple, but in the standard Big Bang model, it's a huge problem. A flat universe is like, well, you use the analogy, balancing a pencil on its point. It's an unstable state.
If it started even slightly curved, either positively like a sphere or negatively like a saddle,
Gravity would have amplified that curvature massively over billions of years. To be this flat today means the initial density, right after the Big Bang, had to be tuned to the critical density with an accuracy better than 1 part in 10 to the 15.
which again sounds ridiculously fine-tuned, like winning an impossible lottery.
Totally. Inflation offers a dynamic solution instead. Think about a balloon, a small, wrinkly balloon.
Okay.
When you inflate it, blow it up massively, what happens to the wrinkles on any small patch of its surface?
They smooth out, the surface looks flat locally.
Exactly. Inflation does the cosmic equivalent. It takes any initial curvature the universe might have had and stretches space by such an enormous factor, like at least 10 to the 26 times, that our observable part just looks incredibly flat.
So A being close to 1 isn't a lucky guess anymore.
It becomes a generic, robust prediction of inflation. Flatness is what you expect after such a massive expansion.
Okay, 2 down. What's the third puzzle? The magnetic monopole problem.
The missing monopoles. So, some very promising theories, grand unified theories or GUTs.
Trying to link the fundamental forces together.
Right. They predict that in the super-hot early universe, exotic, super-heavy particles called magnetic monopoles, particles with just a north or just a south pole, unlike normal magnets, should have been created and created copiously.
Like, lots of them. And they should be stable. Still around today.
Yeah, they should be everywhere. Relics from that early era. But the problem is, we've looked really hard, and we've never, ever detected a single one.
So where are they? Did the GUTs get it wrong?
Well, inflation offers another explanation. Actually, the one Alan Guth was initially working on when he thought of inflation. Simple. What if inflation happened after the time these monopoles would have formed?
Okay. What difference does that make?
The enormous exponential expansion would have stretched space so much that the density of any monopoles created earlier gets diluted down to basically zero.
So they were made, but they're just spread incredibly thin.
Infinitesimally thin. The chance of finding one in our observable universe becomes practically impossible. Inflation just inflated them away, solves the problem without ditching the GUTs.
Wow. Okay, solving 3 massive problems with one core idea. That's pretty
Yeah.
compelling. But how? What actually drives this insane expansion? What's the engine?
Good question. The theory needs an engine, right? And that engine is hypothesized to be a type of energy field filling space called a scalar field. We call this specific one the inflaton field.
A field, not a particle. Like
Yeah.
temperature is a field.
Sort of, yeah.
Yeah.
It has a value at every point in space. Now imagine this inflaton field started off kind of stuck, trapped in a high-energy state, what physicists call a false vacuum. Think of a ball perched high up on a hill, but maybe in a little dip near the peak. It has lots of potential energy just sitting there.
Okay, high potential energy.
So here's the weird part, connecting to Einstein's general relativity. That uniform high potential energy density filling space acts in, strangely. It generates a large negative pressure.
Negative pressure? What does that even mean?
It means it pushes outwards instead of pulling inwards. It creates a powerful repulsive gravitational force. It's like anti-gravity, making space itself expand exponentially fast.
Whoa. Okay, but the ball has to roll down the hill eventually, right? Inflation has to end.
Exactly. For inflation to last long enough to solve the problems, the inflaton field needs to roll down its potential energy hill very slowly. This is the slow roll mechanism. It requires the slope of that hill, the potential to be incredibly flat, almost level.
So the potential energy stays high, driving the expansion, while the field slowly trickles down.
Precisely. The potential energy dominates the kinetic energy.
And then what happens when it reaches the bottom?
Inflation stops. The field reaches its true minimum, its stable low-energy state. It oscillates around that minimum, and crucially, it decays. It dumps all that stored energy into creating a hot, dense soup of the particles we know: quarks, electrons, photons, the standard model particles.
Oh, so that's the bang in the Big Bang, the reheating.
That's the idea. So what does this all mean? It means inflation isn't really a modification of the Big Bang. It's more like a prequel. It sets the stage, creates the hot, dense, uniform, flat conditions that the standard hot Big Bang model then takes over and evolves. The bang is the energetic aftermath of inflation ending.
That makes sense. A prequel that fixes the initial setup.
There's a catch, isn't there always? That extreme flatness required for the inflaton's potential energy hill. That's not something particle physics naturally predicts.
It seems fine-tuned.
It seems potentially quite fine-tuned itself, yeah. Quantum effects would typically make such potentials much steeper. So while inflation solves the fine-tuning problems of the Big Bang's initial conditions, maybe it just relocates the fine-tuning problem to the properties of the inflaton field itself. That's a major theoretical challenge.
Right. But inflation does more than just smooth things out, doesn't it? It has this other incredible prediction. Something about where all the stuff in the universe came from, the galaxies, the clusters.
Yes. This is arguably its most profound and empirically successful prediction, the origin of cosmic structure.
How does that work? Where do structures come from if inflation makes everything perfectly smooth?
Ah, but it's not perfectly smooth. Thanks to quantum mechanics specifically, the Heisenberg uncertainty principle, even empty space, the vacuum, isn't truly empty. It's fizzing with tiny, temporary, random fluctuations.
Quantum jitters.
Quantum jitters, exactly.
Yeah.
And the inflaton field itself would have had these tiny quantum fluctuations superimposed on it. Now, remember, inflation is like a cosmic magnifying glass.
Stretching things massively.
It takes these microscopic subatomic quantum ripples and stretches them to astronomical sizes, faster than the speed of light. As they get stretched beyond the scale of causal connection, they get frozen in.
Frozen.
Yeah, they stop oscillating like quantum waves and become real macroscopic variations in the energy density from place to place. Tiny density perturbations. They shift from being quantum possibilities to classical reality.
These tiny density differences, those are the seeds.
Those are the seeds. The slightly denser regions have slightly more gravity. Over billions of years, they pull in more matter, growing into stars, galaxies, and clusters of galaxies. The slightly less dense regions empty out, becoming the great cosmic voids.
So inflation didn't just smooth the universe, it also created the initial lumps that became everything we see, from quantum fuzz to the cosmic web.
Exactly. A direct causal chain from the physics of the very, very small to the physics of the very, very large. It's an absolutely stunning idea.
And this isn't just a nice story, right? There are predictions here we can actually test.
Oh, yes. Crucially, inflation predicts the statistical properties of these density perturbations. It predicts they should be nearly scale invariant.
Meaning
The initial amplitude, the strength of the fluctuations should be almost the same on all different physical scales. Small scales, large scales, all nearly the same.
Yeah.
Starting bumpiness. Not perfectly the same, but very close.
And have we seen that?
Spectacularly confirmed. This is where the CMB comes in again. It's our most powerful probe.
The cosmic camera. Missions like COBE, then WMAP, then Planck.
They mapped the CMB in incredible detail.
And they found exactly these tiny temperature fluctuations, these anisotropies, at the level of about 1 part in 100,000. That map of hot and cold spots is a direct snapshot of those primordial density perturbations generated during inflation.
So we're literally seeing the seeds.
We are. And when you analyze the pattern, the sizes of the hot and cold spots, you get what's called the angular power spectrum. It has these characteristic acoustic peaks and troughs.
Sounds confident. It encodes a huge amount of information about the early universe. And the key thing is the predictions from the simplest inflationary models that the perturbations are adiabatic, nearly Gaussian, and nearly scale invariant match the observed power spectrum with stunning agreement.
You mentioned nearly scale invariant, not perfectly.
Right. Inflation actually predicts a slight deviation from perfect scale invariance, a specific tilt in the spectrum. And the Planck satellite measured this tilt, the scalar spectral index hands, to be about 0.96.
And 1.0 would be perfectly scale invariant.
Exactly. So 0.96 is a statistically significant phi sigma deviation away from perfect scale invariance in precisely the direction predicted by many inflation models. It's a huge piece of evidence.
Okay, temperature maps look good for inflation, but you mentioned polarization earlier, E modes and B modes.
Yes. The CMB light isn't just different temperatures, it's also polarized, meaning the light waves tend to oscillate in the preferred direction. This polarization pattern can be broken down mathematically into two types.
E modes and B modes, what's
Sure.
the difference?
E modes have this sort of gradient-like pattern, like lines radiating outwards or inwards from points. They're mainly generated by the same density perturbations that cause the temperature fluctuations. We've measured these E modes very precisely, and they also fit the inflationary picture beautifully.
Okay, so E modes come from the lumps. What about B modes?
B modes have a different pattern, more like swirling or curling patterns, like vortices. Now, some B modes can be created later on as CMB light travels through the universe and gets deflected by gravity, gravitational lensing. But primordial B modes, originating from the very early universe,
Yes.
those can essentially only be sourced by one thing: tensor perturbations, which are basically gravitational waves generated during inflation itself.
Ah, gravitational waves from the inflation era.
Exactly. Ripples in spacetime itself, stretched by the expansion. Detecting these primordial B modes is therefore considered.
The smoking gun.
The smoking gun evidence for inflation, yes. Because gravitational waves are a pretty generic prediction of inflation, but not really expected from most alternative theories. Seeing them would be a direct window into that incredible energy scale.
What would finding them tell us? You mentioned a parameter R.
R is the tensor-to-scalar ratio. It measures the amplitude, the strength of these primordial gravitational waves compared to the density perturbations, the scalar ones. Measuring R would tell us the energy scale at which inflation happened. We're talking maybe tenured youth, that's huge, approaching the energy scales where quantum gravity effects become important.
So finding B modes would be finding evidence for inflation and probing physics way beyond our particle accelerators.
Absolutely. But it is incredibly difficult. Remember the BICF2 announcement back in 2014?
Oh yeah, the initial discovery that turned out to be.
Galactic dust. Our own galaxy emits polarized microwave light, especially from dust grains aligning with magnetic fields, and this can mimic the B-mode signal. Separating the faint cosmic signal from this foreground contamination is a massive experimental challenge.
So we haven't found them yet.
No definitive detection yet. The searches have pushed the limits on R further and further down. This non-detection has actually already ruled out many of the simplest inflationary models, the ones that predicted a relatively large R.
Which is good science, right? Making falsifiable predictions.
Exactly. It shows inflation isn't just some vague idea. Specific models make specific predictions that can be and are being tested and potentially ruled out.
Okay, let's shift gears a bit. Inflation solves problems, makes testable predictions, but it also seems to lead to some weirder places. I've heard about the multiverse.
Ah, yes. This is probably the most profound and deeply unsettling consequence that seems to arise quite naturally from many, if not most, plausible inflation models. The idea of eternal inflation.
Eternal, how does that work?
Well, think back to those quantum fluctuations affecting the inflaton field. André Lund, another pioneer of inflation, developed models like chaotic inflation. In these, while the inflaton field is generally rolling down its potential hill, ending inflation, those quantum jitters can occasionally, in some random patches of space, kick the field back up the hill.
Pushing it back into the inflating state.
Exactly. So while inflation ends in our region, allowing our universe to form, other regions get kicked back up and continue inflating exponentially. And from those regions, new patches can stop inflating, forming new universes, while other parts continue forever.
Creating an endless branching of universe.
An infinite fractal-like structure. A multiverse of countless pocket universes, each one potentially emerging from this eternally inflating background sea.
And these other universes, could they be different?
That's the really wild part, because the way inflation ends, the final state the inflaton settles into, could also be influenced by quantum effects or happen differently in different patches. This could mean each pocket universe cools into a state with potentially different physical laws, different fundamental constants, different particle masses.
Wow, so anything goes.
Which leads to the very controversial anthropic principle. Maybe the reason our universe has constants that are so finely tuned for life isn't because they had to be that way, but because in an infinite multiverse, all combinations exist, and we simply find ourselves in one of the ones where observers like us could evolve.
That feels philosophically tricky. Does it even count as science?
That's the heart of the debate. It leads to the measure problem. If you have an infinite number of universes, where literally any physically possible outcome happens an infinite number of times, how do you calculate probabilities? How do you compare theories? If everything happens, what does the theory actually predict for us?
It seems like you can't make predictions anymore.
And that's the core of the falsifiability critique, most strongly voiced by Paul Steinhardt, who, ironically, was one of the original architects of inflation. He argues that if eternal inflation is the generic outcome, and it leads to a multiverse where anything can happen, then the theory predicts nothing specific for our observable universe, and therefore ceases to be scientific.
A pretty stinging critique.
It is. It highlights a deep tension between inflation's successes in explaining our observations and the seemingly unavoidable, untestable philosophical baggage of the multiverse that comes with many of its models.
So despite all the checks in the pro column, solving the horizon, flatness, monopole problems, predicting the right kind of structure,
There are significant theoretical challenges and vocal critics, absolutely.
we already touched on the potential fine-tuning of the inflaton potential itself.
Right. Inflation solves one fine-tuning problem but potentially introduces another. That required flatness of the potential isn't generic in quantum field theory, it seems. Special. Contrived, maybe.
And then there's the inflaton particle itself.
We still don't know what it is. It remains entirely hypothetical. A placeholder for some new physics beyond the standard model. No particle matching its properties has ever been found.
People thought maybe the Higgs boson.
That was an early idea, but detailed analysis showed the simplest Higgs inflation models didn't quite work or conflicted with other data. So now there are literally hundreds of different models of inflation, different shapes for the potential, different ideas for what the influting could be, but no consensus. It's a bit of a theoretical zoo.
Which feeds back into Steinhardt's critique, doesn't it? If you have hundreds of models, can't you always find one to fit the data?
That's part of his argument, yes. That and the multiverse issue rendering it unfalsifiable. He also talks about the unlikeliness problem, that even starting inflation seems to require very specific conditions within the wider space of possibilities.
How have defenders of inflation responded?
Well, there was a pretty public debate, including a letter in 2017 signed by many prominent physicists. They argued that while eternal inflation and the multiverse pose conceptual challenges, individual inflationary models absolutely do make concrete, falsifiable predictions, like the specific value of n's, the tilt, or the expected level of B modes, which are being actively tested and are ruling models out. They argue the framework is scientific and testable, even if the ultimate consequences are mind-bending.
And this unease has also led people to look for completely different ideas, right? Alternatives to inflation.
Yes, most notably the cyclic or ekpyrotic universe models developed largely by Steinhardt himself, along with Neil Turok and others.
It's a basic idea there.
Instead of a single Big Bang singularity followed by inflation, they propose cycles of expansion and contraction. Our Big Bang might have been a big bounce from a previous contracting phase.
Avoiding the singularity and presumably eternal inflation.
That's the goal. These models often invoke more speculative physics, like ideas from string theory, such as colliding higher dimensional membranes or branes. They can potentially solve the horizon and flatness problems through the slow contraction phase before the bounce.
Do these cyclic models have the same observational support as inflation?
Not yet. They are theoretically interesting, but they currently lack the broad body of observational evidence that inflation enjoys, particularly regarding the details of the density perturbations. But here's a crucial difference. Most cyclic or ekpyrotic models predict that primordial gravitational waves should be extremely weak or non-existent.
So they predict R should be very, very small, close to zero.
Exactly. They generally do not expect a strong B-mode signal. This makes the ongoing hunt for primordial B-modes a really critical test to distinguish between the inflationary paradigm and these major alternatives. It's a key observational battleground.
Which brings us squarely to the future. These theoretical debates are fascinating, but ultimately...
they can only be settled by new data. We need better observations.
And that's happening now, right? New experiments coming online.
Absolutely. On the ground, in places like the Atacama Desert in Chile, we have the Simons Observatory, ESTO, starting operations. It's designed specifically to map the CMB polarization with incredible sensitivity to push the limits on the Tensor-to-Scalar ratio, R.
And there's an even bigger ground-based project planned.
Yes, CMBS4. That's envisioned as the definitive ground-based CMB experiment, deploying maybe 500,000 detectors, just a huge leap in scale. The goal is to reach the ultimate sensitivity limits set by gravitational lensing for B-modes, though it's facing some significant funding hurdles right now, with a key decision expected around July 2025.
But we're not just looking from the ground. There's a space mission, too.
Right. To get away from the interference of the Earth's atmosphere, which is crucial for measuring the larger scale B-modes, we need space. JXA, the Japanese Space Agency, is leading the LIGHTBIRD mission.
Scheduled for the early 2030s.
Around that, yeah. It'll orbit the L2 point, like the Webb telescope, giving it a stable, cold environment for an all-sky survey.
And its sensitivity goal.
LIGHTBIRD has an unprecedented target sensitivity of 0.0001. That's incredibly precise. It's sensitive enough to test a wide range of inflationary models, including many that survived previous constraints.
So the next decade or so seems critical. It feels like we're really at a fork in the road.
Completely. There are two main possibilities.
Outcome one, we find them. A definitive detection of primordial B-modes.
That would be historic, Nobel Prize territory easily. It would pretty much cement inflation as the standard paradigm for the earliest moments. Plus, measuring n would give us that energy scale, our first real handle on physics at 10 seconds after the Big Bang, potentially a direct glimpse of quantum gravity effects.
Mind-blowing. And outcome two.
A null result. If experiments like ESO, CMBS4, and LIGHTBIRD push sensitivity down to these incredible levels like more 0.0001 and still find nothing.
That would be huge too, wouldn't it?
Equally profound. In its own way, it would decisively rule out a vast class of the most well-motivated large-field inflationary models. It wouldn't kill inflation entirely. There are other types. But it would dramatically weaken the case for the simplest, most natural versions and lend significant new weight to alternative theories, like the cyclic universe.
So cosmology really is at a crossroads.
It really is. The data from this next generation of experiments is poised to either solidify the inflationary paradigm for decades to come or potentially trigger a whole new cosmological revolution. This raises an important question.
Let's summarize briefly. We've seen inflation's power solving the Big Bang's initial condition problems, explaining the origin of cosmic structure, all supported by amazing CMB data like the temperature fluctuations and the spectral tilt.
But we've also seen the challenges, the unknown identity of the inflaton, the potential fine-tuning of its properties, and the deeply weird, perhaps untestable consequences of eternal inflation in the multiverse.
So here's a final thought for you, the listener. Imagine you are part of a generation that might witness the first direct glimpse of quantum gravity in action through B modes, or, conversely, witness the overturning of our leading theory of cosmic origins if they're not found. What does that tell us about the scientific process itself? This constant pushing against the edge of what's knowable, daring to ask the biggest questions about where we came from, even when the answers get strange or uncomfortable.
It's a remarkable time to be studying the universe.
Absolutely. Thank you for bringing these incredible sources to the deep dive. This journey into the very beginning of everything has been truly fascinating.